Hello, everybody. Welcome to our Capstone project, Test Operation Integration with a Machine Execution System. Our sponsoring company is Cambridge Technologies, and our technical directors are Jonathan O'Hare and Sean Mitra. Our team consists of myself, Alec Goldberg, Computer Engineering, and Ryan Bradley, Electrical Engineering. Now, a little bit about Cambridge Technologies. Cambridge Technologies designs and manufactures cutting-edge laser steering beam solutions. These include polygon optical scanners, galvanometer optical components, high-powered scanning heads, and finally, controlling hardware and software. Now, for our project specifically, we're going to be focused on Cambridge Technologies' highly engineered line of galvanometers. These galvanometers are built around a highly optimized moving magnet rotor, making Novanta the industry leader for these components. Now, these are some of the uses for high-powered galvanometers, such as via-hole drilling and high-speed marking and engraving. Now, we know how a galvanometer works, but you might be wondering, how does this relate to our project? As we learned earlier, galvanometers rely on this magnetic field, specifically a permanent magnet, which begins to change properties at high temperatures. As Cambridge Technologies works on progressing their technology and making these galvanometers faster, temperature becomes a problem. For the hardware side of our project, we'll be making a complete test bench to ensure the quality of our magnet, using lasers to measure the tri-dimensional bending under high temperatures.
Okay, for our anticipated best outcome, this project has not been achieved, and the purpose for this outcome that there will be two manufacturing operations, essentially a test measuring device and an input device that needs to be integrated into the MES system. The input device would upload the data into the electronic traveler so it can save the result from its procedure. In addition to this outcome, it requires to have the devices reboot in a production environment, having the HMIs or the human machine interference acceptable through the MS UI environment with instructions and support for the operator, and it may require minimum user training to get used for its operation of the system. On this flowchart, it represents the operation of the testing structure. It starts with loading the workpiece. Once it is loaded, it needs to be aligned to the laser so the laser can be detected on a sensor to measure its X and Y position. Finally, the heating cycle will begin by heating the workpiece and then let it cool off after gaining enough data. And a sample time is like a period to heat the workpiece so its temperature can reach to the set point temperature of 100 degrees Celsius. Once the heating cycle is completed, the workpiece can be removed and its testing procedure is completed. To understand a little more of how the hardware works based on the flowchart we talked about earlier, the laser diode will emit the laser and a mirror is attached to the workpiece so it can reflect the laser, and the laser will travel to the PSD sensor to measure its position, and its data will be transmitted to the MS workstation. The other device that is also connected to the workstation is a thermocouple, in which will measure the workpiece temperature. With the temperature and the position data collected, it will be compiled to the database, and the induction heater will require a switch to control its power so the workpiece will not be overheated during the heating cycle. Now, on this sketch, the schematic shows of how the testing structure will look like. The main structure are made out of aluminum extruders so it can hold the components, and the components inside the structure will be used to measure the workpiece temperature and position. In comparison to the flowchart we talked about earlier about the hardware, the laser diode and the sensor are close to each other with a slight angle for the laser to be reflected from the workpiece mirror. The thermocouple is close to the heated workpiece so it can measure its temperature due to correlation when adding an insulator midway of the workpiece. The power adapter is the source of powering the induction heater, or it has uh, sorry, a knob so it can adjust its voltage, well, it needs to be powered at its maximum for its fast heating rate. And the laptop itself, it contains the workstation, so it can use the tool program to upload its position and temperature data of the workpiece. And finally, on these two images, these two represent the comparison of the testing structure that we had accomplished back in fall and later on this spring. On the original structure, you will see on the left, we have accomplished to build the structure with integration to only the PSD sensor and the laser diode. And on the next image, we made more accomplishments to modify the structure along with integrating other components so we could be able to develop the heating cycle and to measure its data on the workpiece.
So moving on to the software side, 80% of traditional manufacturing systems use a paper trail, use paper trails to record the data. And we all know that big stacks of paper can get out of control quickly. Not only is it unorganized, but there's also no streamlined method to analyze our data and ensure the quality of our products consistent. So for the software side of this project, we will be building an intelligent machine execution system to go along with our test bench. This will be designed to gain versatility and to organize, control, and monitor processes in an easy and accessible way. With an MES system, we are able to streamline all of our processes and data into a database and use this information to implement better quality control, in addition to opening the door to machine learning. So our anticipated best outcome is a human-machine interface that will autonomously handle input and output signals, data acquisition and storage, back-end calculation, and finally data analysis to determine if the workpiece can move on to the next step of the production line. So here we can see a simple block diagram of the software and how it works with the hardware in unison. So the first thing is the user will load the workpiece into the directed slot. We will be using the PSD sensor, which is just a positional sensor that tells you where a laser is. We will see if that's zeroed out to begin with, and then if it is, we will begin our heating process. And throughout the heating process, we're taking data every second. We're taking our X position, Y position of data, and at the end, we'll be able to use all of these calculations to calculate different magnitudes and see how the position has changed over time. And from there, we can make our calculations and upload them to a database, in addition to a user interface, as we'll see here. So for our project, we're trying to take this process and make it super automatic to allow an operator with minimal training to be able to operate it. So once our user selects begin, all the necessary calculations will be done on the back end, eliminating the need for a technical background to operate this. Another key feature that we have is an authentication system that creates a security wall for operator. This uses the badge number, which will get matched to the corresponding logged in user, and either deny or allow based on the records. Now, to program this HMI, we have been giving a machine execution system software, which uses a Node-RED programming language for all the user graphics. As mentioned earlier, 90% of our data flow and calculations are handled on the back end. However, we still need the signal to begin the program in addition to sending data back and forth, such as the final calculations, serial numbers of the product, user info, and much more. So now for the meat of our project. We're using a variety of sensors to get all of our necessary information. This includes a thermocouple, PSD sensor, a PID controller, and for the backend, we're actually using Python as our main programming language, where we perform all of our data acquisition. To begin, we are taking an initial PSD sensor reading to realize the initial position of our workpiece. We then send a signal to our induction heater to turn on. Our thermocouple is an indicator for when the workpiece reaches the desired temperature, and then we can begin taking values. This gives us X and Y values, and then using the displacement of the values, we can calculate the change in magnitude, the minimum magnitude, and the final magnitude. This tells us how much our workpiece has moved, and if it has bent too much, it can't move on into the next step of the manufacturing line. And throughout each step, we're storing all the data into a time series SQL database. This allows us to retrieve values at desired timestamps, eliminating excess data. In addition to this, each data point is correlated with the serial number. So an operator can always go back and look at the data for each serial number. Now here we can just see an overall full process. Once again, we can see that the operator is going to enter the serial number of the workpiece, hit enter. This signal is then sent to our backend, which cross-checks the validity of the serial number against the database of products. And then we can start taking our readings. But first we need to make sure that our workpiece is in range of the sensor, meaning that our workpiece is in the right place and ready to go. If this is true, we begin our process, which turns the induction heater on, and we collect all the data. As soon as we hit our desired temperature, whether it's 80 degrees or 100 degrees Celsius, we can cross-check the minimum, maximum, and change in magnitude and display this on the user interface. In addition to this, we generate a highly detailed visualization in which each of the spikes will notify the user whether there has been issues or what sort of pattern is going on with the workpiece. Now, from there, the operator is able to determine if the workpiece is faulty.
Okay, for the presentations that I have accomplished for the hardware side, I have performed multiple testing to develop the heating cycle and requires only the power adapter, and the temperature measurements are being correlated when you're measuring temperature on three different areas when you upload an insulator in between of the workpiece. One of them will be on top and on the bottom, and the induction coil itself, and the components that are being adjusted to allow the workpiece and the laser to be aligned for the PSD sensor. And the thermocouple's position is also has been adjusted so we'll be able to get good accuracy for the temperature on the workpiece. For further information of how the hardware really works, the induction heater is been integrated to the power adapter, and it needs to be adjusted up to its maximum voltage. The maximum voltage is about 12 volts, and it will allow the induction heater to have the highest heating rate to heat the workpiece. And while automation cannot work for this process to control its power, the voltage will reach to the maximum when you adjust the knob itself on the power adapter. And after I did some multiple testing on the induction heater with only the power adapter, it needs to be activated for only 1 minute so you can heat the workpiece up to a set point temperature of 1 degree Celsius. In addition to that, which is not shown on the image, we also upload a lubricant light so it could be adjusted, integrated to the power adapter so it can alert that the induction heater is activated. And we earlier mentioned that if you have two different components connected to the workstation, so we can pick up measurements on the workpiece position and temperature. Both of these devices are already been integrated to the induction, the testing structure, while both the laser diode and the workpiece are currently alike to each other, so we get accurate readings for the workpiece position. And apparently, we are unable to integrate a cooling fan on the structure, but it would take time to allow all the equipment, including the workpiece itself, to cool off for, I would say, at least 5 minutes.
So, in conclusion, throughout this year, we have been able to accomplish a lot. And although we didn't completely achieve our anticipated best outcome, which in our case means that our testing structure was just not ready for the production environment. However, what we have been able to accomplish is a fully automated testing process for an operator with the user interface that we mentioned earlier. We are able to record and process all of the data within the temperature range. And finally, we're able to calculate the final results to determine the quality of the workpiece. And on the hardware side, we're actually able to find the correlation temperature measurements between the induction heater to get accurate measurements, in addition to adjust components for tulip and testing hardware with only a power adapter. We want to give a special thank you to our technical directors, Jonathan O'Hare, Sean Mitra. We'd also like to thank our Capstone director, Dr. Harish Sunak, for all of his support, and finally Brendan Smirbeck for all of his good advice. It wouldn't have been possible without you guys. Thank you.